talk about the recent progress in some class of the non-homogeneous, fully nonlinear problems with kind of degeneracy. Before presenting our main results, let me present some motivations. In the universe of the elliptic PDEs, I will consider three classes: the uniform elliptic models, second order operators of the single degeneracy law in the gradient variable, and the double degeneracy law in the gradient variable. In these three classes, I will consider two sets: the problems in divergence form and problems in non-divergence form. In divergence form, a typical uniform elliptic model, it's the divergence of a matrix AX times the gradient. In non-divergence form, we have the trace of a uniform elliptic matrix times the Hessian of the U. For the single degeneracy law, a typical example is the P Laplacian operator. Then in this case, we consider the degenerate case, the P greater than 2. For the non-divergence structure, a typical example of single degeneracy law is you collapse the uniform ellipse of the operator by a p power of the gradient, when the power is the positive power in this case. In the divergence form, a simple example of the double degeneracy law is the PQ Laplacian. The PQ obeys this monotonicity. The modulating function A here, it's the non-negative and continuous profile. Then in this point arises the following natural question: what should be the model case in the non-divergence form? The typical model case in this scenario is you collapse the uniform ellipticity of the uniform elliptic operator times this vectorial function, where the PQ obey this monotonicity order. The modulating function I, it's a non-negative and continuous profile. This kind of operator is exactly the counterpart of some variational problems from the calculus of variations with double phase structure. Functionals of double phase structure are functionals in this appearance. The minimizers of these functionals are solutions of the PQ Laplacian. This class of problems is important in applied science because play a fundamental role in material sciences, application in elasticity theory, and the transition flow, among other areas. I can cite some recent and old contributions, for example, in this class of problems by due to Cristiano De Filippis, Paulo Marcellini, Giuseppe Mingione. The old contributions, you can take a look in the Uraltseva and Urdaletova manuscripts, and the Zirkov for the first one that related this class of problem of the material sciences, for example. Then we are interested in studying fully nonlinear models and understand quantitative properties of the solutions in this kind of the PDEs. In our setting, the right hand side, the source term, it's the bounded EL infinite profile. The second order operator, it's a capital lambda elliptic operator. What means this? It's the Lipschitz function in the variable of the symmetric matrix. The coefficients of the operator enjoy a modulus of continuity. The non-degeneracy law, double degeneracy law in our problem, it's comparable above and below for this vectorial function. In the PQ, L1, L2, and the A obey this property. The modulating function, it's non-negative, it's a continuous profile. Before about the regularity aspects of the problem, let me once again present some motivations. When you consider a PDE in general, consider the perturbative arguments that will use, you must consider two important aspects in this approach. The first one is the corresponding a priori estimates to homogeneous problem with frozen coefficients. The homogeneous problem, this problem when the right-hand side is trivial, it's zero. The frozen coefficient is exactly when the matrix is constant. The matrix AX equal the matrix X0 for all X. The other important aspects in this theory is the integrability of the right-hand side. These two things together provide a classification scheme of the solution in the following sense. Consider this scaled and normalized profile, and the power kappa belongs the range 0 and 2. Then we verify what the PDE, the V satisfied. V does not satisfy the same PDE, but satisfies a PDE with the same properties in the following sense. The coefficients of the matrix enjoy a similar modulus of continuity. In the right-hand side, the new right-hand side remains in the same integrability space, provided the power kappa is selected in an appropriate sense. In summarizing, we can provide the exactly modulus of continuity of viscosity solution in this case, provided the integrability of the right-hand side is in a suitable range. For example, if the range of the integrability of the right-hand side is between the dimension over 2 and the dimension, solutions are C1 var sigma for explicit var sigma. For example, with the integrability of the right-hand side is greater than dimension, then solutions enjoy a gradient continuous. A viscous solution is exactly a continuous solution such that we can test it by C2 function in this way. This classification schemes is a natural extension of the recent work due to Daskalopoulos, Kuzminjoni, and Teixeira. But what happens regarding the classification schemes when you consider the fully nonlinear models with double degeneracy signature? Recently, Cristiano de Filippis proved C1 gamma estimates for bounded viscous solution of this class of problems. Berindelli de Menger proved similar results for the single degeneracy law for the degenerate and singular case. The singular case, it's exactly when the P is greater than -1 and 0. And the Invert Silvestri proved C1 alpha estimates for the single degeneracy law when the modulating function is true. Nonetheless, the Cristiano de Filippis manuscript leaves some open questions. For example, what is the exactly modulus of continuity when the right-hand side is L infinite? This is one of the motivations in the main contributions of our work. Show the exactly modulus of continuity for the bounded viscous solutions. For the uniform elliptic setting, the contributions dates back to the Caffarelli and Trundinger classical results. Then in our classification scheme, we can provide the following results. Under the structural assumption, solutions of our problem is C1 minimum of this power 1 over P plus 1 and alpha homogeneous minus. Alpha homogeneous minus, these notations means the following. We can select any number between 0 and alpha homogeneous. The alpha homogeneous is the Holder exponent of the solutions of homogeneous problem with constant coefficients. In this point, I can stress three main differences between our approach and the Cristiano de Filippis strategy. For example, in order to obtain compactness for the solution, Cristiano de Filippis make use of Ishilion's method. We can prove a compactness of solution by proving a Harnack inequality, for example. The C1 alpha regime is assessed by Cristiano De Phillips by using a very interesting idea that dates back to the Invert Silvestri manuscript. It's exactly deviation by plan. Deviation by plan is considered this translation problem. And regarding the degeneracy character of the operator, the Phillips consider two regimes. When the C translation is small and large. In our case, we consider two regimes, but when the gradient of the solutions are small in a suitable and appropriated controlled sense, and when the gradient of the solution is large. And this is exactly our main result, one of the main results in our manuscript. This is a joint work with Gleidson Chaves Riccardi from the Universidade Federal do Ceará. It says the following: let me compact the subset of the B1 and the bounded viscous solution for our problem under the structural assumption. Then, any solution of this problem, it's locally C1 alpha, where alpha is this exponent here. This exponent. Moreover, the C1 alpha same norm has a universal control. It's controlled by a universal constant times the L infinite norm of the solution times plus the L infinite norm of F to this power plus 1, where these quantities is exactly a C1 alpha same norm LX, L sub index X0, it's exactly the Taylor expansion of U up to the first order. This theorem is a natural extension by making use a different approach of a recent paper by Damião Araújo, Gleidson Riccardi, Eduardo Teixeira. It's important to highlight the aspects, the implications of obtaining the sharp regularity for this kind of problem. For example, as a consequence of these results, we can prove blow up and Liouville type results. It's exactly global classification of global profiles with geometric properties and house of measure estimate, sharp regularity, and certain free boundary problems. For example, Bernoulli, obstacle, singular perturbator, among the others. Here I listed some examples of these applications in many free boundary problems. And today in the afternoon, Gianni Ramparso, we will talk about application of this kind of problem in a Bernoulli type problem, a free boundary problem. And before presenting the strategy in order to obtain our estimates, we can make use the following auxiliary tools. For example, the maximal principle, the L infinite norm of the U is bounded for the L infinite norm of bounded data plus universal constant times this amount. The holder estimates the C alpha prime norm of U, it's bounded by universal constant times this amount. The stability results says the following: if you have a family of a sequence of the problems, when the UK converge in some sense, FK, the right-hand side of your PD converge, in the family of the operators converge everything in suitable sense, then you can pass the limit in the equation. This is a typical stability result. Invert Silvestri cutting limits, a very important tool in this problem. It says the following: if you have a homogeneous problem to the fully nonlinear problem with double degeneracy or single degeneracy, we can, any solution of this problem, it's a solution for the uniform elliptic operator, the homogeneous case, of course. Roughly speaking, we can remove the degeneracy law of the problem. And finally, we make use the Phillips regularity estimates. You know, a priori, the solutions are C1 gamma for some gamma, but our contribution is provided a explicit expression of such n gamma. Some of these two were proved in the Cristiano de Phillips manuscript or in this recent joint work with João Vivas. And the first step in assessing C1 alpha estimates its proof is to prove approximation lemma. The approximation lemma says the following: give me a normalized profile and an error. Then there exists amount such that whenever the coefficients of the operator, the right-hand side, it's small enough, then we are able to find a F harmonic function epsilon close in the C1 topology to your function U. The F harmonic function is a function of the homogeneous problem with constant coefficients. After removing the F use the inversive vesicity, let me remove the degeneracy signature of the problem. In other words, do you put close you close a profile with good a priori estimates. Then in some sense you can transfer or transport the a priori estimates of P to U. This is the heuristic behind the regularity scheme. Then the proof is based on reduction ad absurdum argument and use compactness, stability, a priori estimates, the inversive cutting. It's by now a classical proof by contradiction. The approximation lemma provides a good geometric decay in the following sense. The approximation lemma implies that U profile is close in a C1 alpha fashion to its tangent plane. This is exactly the content of this lemma. Then you can put U close to its tangent plane in a C1 alpha fashion. The next step is iterate this geometric scheme. Then we can invoke if you were able to prove this geometric decay, then by invoking a Dini-Campanato embedding, then solutions are C1 alpha and the point x0. But what's the problem here? This map is scaling the normalized profile for our class of problem. It's not invariant by our second order operator, because the problem is exactly the double degeneracy law in this case. But in order to overcome this problem, we do this geometric iteration, consider this geometric scheme. It's a new oscillation mechanism, which take into account the influence of the magnitude of gradient of U inside the geometric iteration. This is the Fritz scheme of the interaction. This is the K step of the induction. And with this scheme, by split the analysis in two cases, where the point is inside the singular zone. Inside the singular zone, it's exactly the points inside V1, such that the gradient is bounded in a suitable sense, suitable appropriate sense. Inside the singular zone, we can prove the exactly C1 alpha geometric estimates for this problem. And what happens outside the singular zone? Outside the singular zone, the gradient is, roughly speaking, large and has an upper bound, because you know a priori, due to the Cristiano de Phillips result, the gradient is continuous. The gradient is continuous, this is an upper bounded control. Then the gradient is bounded away from 0 and infinity. Then, roughly speaking, the problem becomes a problem with a uniform elliptic structure. With this structure, you can invoke the Caffarelli-Trindle classification classical estimates. For example, with these outside the singular zone, we can prove the sharp regularity estimate for this case. A simple application in this case, coming back to the double phase problems under these structural condition. Here in the modulating function, it's non-negative, it's C1 beta. Then consider a minimum of these Euler-Lagrange functionals. Minimizers are solutions of the PQ Laplacian. Then by invoking a recent result by Maria Colombo and Giuseppe Mingioni, minimizers are locally C1 alpha C. Then in this case, we invoke equivalent result of notions of weak solution by Fang and Zhang. That says the following: n weak solution of the PQ Laplacian is indeed a viscous solution. Then we can decompose these operating in divergent form in its non-divergence form. Then we can, this good part, it's a G1. G1 is exactly a second order operator of the double degenerate signature. J2, it's the bad guy, the bad part of the operator. Then we pass the bad part for the right-hand side. And under a suitable control of the J2, we can invoke our previous main results in the following sense. If the normalized infinite Laplacian, the gradient of the modulating function, the gradient of the function, it's L infinite profile, then we can prove a sort of CP prime regularity of these minimizers of double phase problem. This is an application of our results. Finally, I would like to stress we can classify in this table almost all the integrability regimes. We have this open problem here when the integrability is greater than dimension, but the other case we can provide an exact answer. But natural question arises here. What happens when the right-hand side is a suitable power of the? This is exactly the class of the dead core problems. Dead core problems, it's a non-negative solution that vanishes inside a priori unknown region and does not violate the strong maximal principle. It's exactly zero, but it's not trivial. Then we can looking for better estimates along free boundary points. Free boundary points is actually the boundary of the region, the non-contact region. In this setting, we can prove exactly this improved geometric decay around free boundary points. Give me a free boundary point, a radius is small enough, then you decay in this order. R, the radius of the ball, to the power p plus 2 over p plus 1 minus mu. This power is a magical power in the following sense. This power is exactly greater than the power 1 plus 1 over p plus 1, which is the better regularity estimates in this setting when you consider the structural assumption plus concave convex or asymptotically convex operator. Then for the dead core problems, we can prove an improved geometric decay along free boundary points. When you combine the previous result and this result, we can prescribe exactly the behavior of n solutions of the dead core problem close the free boundary. The solutions are trapped between two specific surfaces. And finally, in order to finish, let me present the recent progress in this class. We can consider the global, we can prove global regularity results for this class of problem in some balanced degeneracy of the variable orders. We prove, for example, existence, uniqueness in uniform boundless. global compactness, gradient estimates, improved local and sharp global results, a sort of geometric non-degeneracy, and finer estimates in many applications and free boundary problem. This is exactly extensive recent results due to Brinderi de Mengel, Annie Bronzi, Edgar Pimentel, Jenny Rampasso, Eduardo Teixeira, and the Fang Radulescu. These results we can found in this article in the archive. Thank you very much for your attention.